Hello and welcome to the course Design and Analysis of Algorithms. Today we will be discussing hashing. Many applications deal with a lot of data stored in some form of a table containing information. For example, a telephone directory has fields name, address and phone number. To find somebody's phone number, the book is searched on the name field. To find the entry in the table, the contents of one of the fields is required. We do not need to know the contents of all the fields. The field used to search the contents of other fields is called the key. Ideally, the key should uniquely identify the entry. That is, no two names in the telephone directory should be the same. The table formulation can be treated as an abstract data type that is composed of a collection of key value pairs such that each key is distinct. The storage size is dependent on the number of distinct keys. A set of operations that can be defined on this abstract data type are insert, search, and delete. Given an abstract data type, what would be the complexity to perform these operations? In an unsorted array, the insert operation will take constant time as we can place that element at the end of the array. The search operation in an unsorted array will take at most n operations as we will have to perform linear search. And similarly, the delete operation in an unsorted array will take at most n operations, as in the worst case, all elements may have to be moved. For sorted array, the insert operation can take up to n operations, as to maintain the sorted array, all the elements may have to be moved. The search in unsorted array can be performed in log n by using binary search, and the delete operation can also take up to n operations, as in the worst case all elements may have to be moved. In an unsorted linked list, the insert operation will be performed in constant time, as the element will be placed at the head of the linked list. The search operation in an unsorted linked list can take up to n operations, as the element we are trying to search can be at the end of the linked list. Similarly, the delete operation will take n operations, as we will have to search the element first and then delete it, and the search operation takes n operations. In a sorted linked list, the insert operation can take n operations, as it can be the largest value that needs to be placed in the tail of the linked list. Similarly, the search operation can take at most n operations, and delete also can take up to n operations. An ordered binary tree is a rooted tree with the property that the key in the left subtree is less than that of the root, and the key in the right subtree is greater than that of the root. And the left and the right subtrees are ordinary binary trees, or ordered binary trees. So in an ordered binary tree, the insert, search, and delete operations will take log of n time, which is the height of the binary tree. As in the worst case, we have to place the item in the leaf of the tree. Frequently used applications today deal with a lot of data, and there are countless lookup operations that are time critical. As we have seen in the last slide, that the best we can do for insert, search, and delete is log n. So as the data becomes large, this value of log n operation becomes significant. In general, we need something that can do better than log n. So we need lookups to occur in near constant time. Solution to this is hashing. Hashing is a technique that maps set of key value pairs into a hash table of size m. A hash table is a data structure that stores key value pairs and has two components, a hash function and an array. Hash function is applied to the key to determine the index of the key value pair in the hash table. Each key is mapped to an index in the range from 0 to m minus 1, where m is the size of the hash table. Ideally, We like to have a one-to-one map, but it is not easy to find one. The array holds all the key value entries in the table. The entries in the array are scattered and are not stored consecutively. To see how hashing works, let's have a look at this example. We are given 5 key value pairs that we have to place in the table of size 8. So we define a simple hash function that is based on modulus arithmetic, and we take mod 8 so that these values can be placed in one of these 8 locations. So where will the data be stored? So let's start off with the first value, where the key is 22. So 22 mod 8 is 6. So we place the first key value pair in the 6th location. Then 33 mod 8 is 1. So we place the item in the first location. 3 mod 8 is 3. So this will be placed in the third index. 72 mod 8 is 0. So this will be placed in the 0th index. And 85 mod 8 is 5. So this will be placed in the 5th index. So what if we need to insert the following new key value pairs? If we compute mod 8 of these three numbers, we get the index location 1. They all map to the same location. So obviously H is not a good hash function. This is called collision. Two or more keys hashing to the same slot leads to collision. When collision occurs, we need to handle them, as we cannot place two numbers in the same location. Collisions can be reduced by choosing a good hash function, increasing the size of the hash table, and devising a mechanism to deal with these collisions. So how should we choose a good hash function? A good hash function must have the following properties. It should be easy to compute. So the computation time of the hash function should be in constant time. It should avoid collision. It should distribute data uniformly over the range of available addresses. It should generate the same hash value when applied to equal objects. And it should generate different hash values when applied to unequal objects. And it should generate a hash value independent from any patterns that exist in the distribution of the keys. And it should generate a very different hash values for similar strings. For example, the hash value of PT should be much different than the hash value of PTS. So how do we find a good hash function? In general, we cannot. There is no such magic function. In some specific cases, where all possible values are known in advance, it is possible to compute a perfect hash function. What is the next best thing we can do? A perfect hash function would tell us exactly where to look. In general, the best we can do is to choose a function that tells us where to start looking. In the next few slides, we will look at some methods that can be used to define hash function. The first method is the truncation method, in which we ignore the part of the key and use the remaining part directly as the index to the hash table. For example, if we have 8-digit keys and the hash table has 1000 entries, then the last 3 digits can make the hash function. We require 3 digits here, so we need index between 0 to 999. So if we have 100 entries in the table, we would only require 2 digits. So in this case, we have 1000 entries, so we will be taking the last 3 digits. If we look at this example here, we have this number. We just take the last 3 digits, and that will be the index to the key value pair in the table. So the disadvantage of truncation method is that it does not always distribute the keys uniformly. The next is the folding method, in which we break the key into parts of equal length and combine them in some way. For example, if the keys are 8-digit numbers and the hash table has 1000 entries, we can break the key into 3-digit parts, add them up, and if necessary, truncate them. Let's have a look at this example. We have an 8-digit number. We break them into 3 parts of 3 digits. Since the 8 cannot be divided equally into 3, one of the part has to be of 2 digits. We add these up and we come up with the number 1016. Since we need only 3 digits, we can take the last 3 digits of this number. So our index to the table for the key value pair would be 016. Folding method is better than truncation method. Another method is the MidSquare method, in which we take the square of the key and take the middle digits from the squared value. For example, if the keys are 4-digit numbers and the hash table has 100 entries, we take the square of the key and pick the middle 2 digits as the index to the hash table. For example, if we have the number 6445, so the hash function will be that we square this number and take the middle 2 digits of the squared value, which is 38. So our index to the hash table will be 38. Another method is the division method, which uses the modular arithmetic that if a hash table has m slots, to map a key k into one of the m slots, we define the hash function as hash of the key value is equal to the key value mod m, as we have already seen in the previous slides. The advantage of this function is that it is fast and it only requires a single operation. The disadvantage is that not all values of m are suitable for this hash function. For example, we need to avoid powers of 2. Generally, good values of n are prime numbers that are not very close to power of 2. If a given key is a string instead of a number, we can use the ASCII code of each character of the string to build a hash function. In this example, we multiply the ASCII code of each character with the increasing power of some prime number, and then taking the modulus of that table size so that data can fit in this table size. Suppose our key is Ali. We take the last character, the ASCII code of that is 105. So we multiply that with 37 to the power of 0, which is 1. So we have 105 times 1, then plus the code of L is 108. 108 times 37 to the power of 1 plus the most significant character is A, that has a code of 97. So we multiply that with 37 to the power of 2, or 37 square. Since the data we have, or the table size we have, is 1000, here we choose 1009, which is the closest prime number to 1000. So that is our hash function. So we apply this hash function to Ali and we get 679. So if we have key Ali, we apply a hash function to it, so it will be placed in the location 679. One of the important factors that play an important role in frequency of collisions is the hash table size. Given a hash table with m slots and n elements stored in it, we define the load factor of the table as lambda equal to n divided by m, which is the ratio of number of elements in the hash table to the size of the hash table. The load factor gives us an indication of how full the table is. The possible values of the load factor depends on the method we use for resolving collisions. When a collision occurs, we need to find the location to put one of the records. The two approaches to resolve collisions are separate chaining and open addressing. The three methods that can be used for open addressing approach are linear probing, quadratic probing, and double probing. For separate chaining, the idea is to put all the elements that hash to the same slot in a linked list. The slots contain a pointer to the head of the list. For example, we are given the following keys and a hash function of key modulus 10. So in this case, 81 and 1 are mapped to the same slot. So they will be added to the linked list and so on. So we define a load factor lambda of the table that indicates the average number of elements stored in the chain. In this case of separate chaining, lambda can be more than 1 as the number of elements can be more than the size of the table as we are forming the linked list for each slot. For search and updates, a good hash function is still needed to distribute the keys evenly. So the size of the hash table should be small enough not to waste space, and it should be large enough such that the list in each slot remains short. When using separate chaining, to perform an insert operation, the slot in the table is located using the hash function, and then the key is inserted to the head of the linked list at that slot. To perform the search operation, the slot in the table is located using the hash function, and the key is searched in the linked list headed at that slot using linear search. And for delete operation, the slot in the table is located using the hash function, and then the key is deleted in the linked list headed at that slot. The advantages of separate chaining are that average case performance stays good even when our load factor is greater than 1. We have a better space utilization for large number of items, and more items can be stored in the using separate chaining than the hash table size, and the delete is easier to implement than the open addressing. The disadvantages are that it requires dynamic data. It also requires storage for pointers in addition to data and can have poor locality, which causes poor caching performance. Keeping in mind that the load factor measures how full the table is, it also indicates the average number of elements stored in the linked list. So given a load factor lambda, we would like to know the best, average and worst case of new key insert, which is also same as unsuccessful find because the key would only be inserted if it's not already in the linked list, and successful find. The best case for all cases will be order of 1, that is, it is placed in the head of the linked list, and the worst case is n for all cases because all the keys can be placed in the single linked list in the single slot. The average number of comparison for insert or unsuccessful search is 1 plus lambda. The 1 is for locating the slot and lambda is the average size of the linked list. In successful search, on, on average, half of the keys in the linked list containing the target key is searched before finding the target. So the average number of comparison for successful search is 1 plus lambda by 2, which is again 1 plus lambda. If n is big O of m, then lambda is big O of m. And the total time for search, insert and delete is big O of 1, independent of the size of n. When using open addressing, the idea is to store all the elements in the hash table itself. If a collision occurs, we find another slot. When searching for an element, we examine slots until the element is found or the element is not in the table. It is possible that the table is full and a new element cannot be inserted. In that case, we resize the hash table and rehash the values. The sequence of slots to be examined or probed is computed in a systematic way. There are three common ways to determine a probe sequence: linear probing, quadratic probing, and double probing. When using linear probing, if we want to insert an item and a collision occurs, we place the record in the next empty slot found using linear search. Upon reaching the end of the table, we continue searching from the start of the table. For search operation, the probe sequence is same as the insert operation. We have three cases here. The first case is slot in the table is occupied with an element of the equal key. That is, we have found an item that we were looking for. The second case is the position in the table is empty. It means that the item we are looking for is not in the hash table. If it was in the hash table, we would have found it before reaching the empty slot. And the third case is position in the table is occupied with a different element, which means that two elements have the same key but the value is different. So that is not the item we are looking for. So we will move on using the linear search to the next elements or the next slots until we have found the value we are looking for. The deletion is a bit tricky. We can't just delete a record that is involved in collision. That is because we will not be able to find all the items that are placed after the empty slot that we have just created. So for delete operation, we use lazy delete. We just mark the item as inactive rather than removing it, so that when we are searching for it, we will see the inactive status and we know that it has been deleted. And if we want to insert some item, we know that this item has been deleted. We can just place the new item in this slot. So the deleted slot can later be used for insertion. Let's look at an example of open addressing using linear probing. We have 5 items that we need to insert in the hash table of size 10. In this case, our hash function will be key value mod 10. We start off with the first value of 89 and take mod 10 of 89, which is 9, and we go look for the 9th index here, which is empty. So 89 will be placed in the 9th index. The next item is 18. We take mod 10 of 18, which is 8. The 8th slot or the 8th index is currently available, so we place 18 in this slot. Next value is 49. We take mod 10 of 49, which is 9. Now the ninth location is already filled. So where would the 49 go? So we look at the next location of 89. Since it is the end of the table, we go to the start of the table. So the first location we find empty, we will place 49 over there. After that, we need to insert 58. We take mod 10 of 58, which is again 8. So the 8th location is already occupied. So we look, using linear searching, we look at the next slot, which is already occupied. We look at the next slot, which is also occupied. Then we look at the next slot, which is empty. So here, the first slot is empty. We will place 58 in this first slot. Similarly, the last item 9, we take mod 10 of 9, which is 9. In this case, the ninth location is already occupied. We look at the next two locations or slots which are already occupied. So the third slot is empty. Third slot from the ninth location, the actual slot is the second one, which is empty. So we place 9 in the second slot. So to summarize, if a collision occurs, we keep on searching the next slots until we find an empty slot and we place our current value in that slot. An issue with the linear probing is that it has a tendency to form clusters. A cluster is a group of elements stored consecutively in the hash table without containing any empty slots. The bigger a cluster gets, it starts taking more time to find a free slot or to search an element. Additionally, it becomes more likely that the new value will hash into the cluster and make it even bigger. Even if the table is relatively empty, clustering is still possible. This effect is known as primary clustering. In linear probing, if all the keys are mapped to the same index, we would need to probe over all n elements. So the worst case time complexity of insert, search and delete operation is big O of n. If there is no collision, the cost of insert, search and delete operations is big O of 1. For average case complexity, the formal proof is too complex for the scope of this course. For insert, search and delete operations, the average case is big O of 1. Generally, it is better to keep the load factor under 0.7. If the load factor gets high, double the table size and rehash. For quadratic probing, the collision is resolved by examining certain cells away from the original probe point. For that, we use quadratic function of I square. If the hash function evaluates to a slot S, which results in a collision, we probe the slot S plus 1 square, then S plus 2 square, and so on. So that means we first examine slot 1, then slot 4 and slot 9. So in the case of linear probing, we were examining slot 1, 2, 3 and 4 and so on. But in this case of quadratic probing, we are examining the slot of 1 square, 2 square, 3 square and so on. So the subsequent probe points are a quadratic number of positions from the original probe point. Quadratic probing eliminates the problem of primary clustering. Let's use quadratic probing in this example to insert the 5 keys given in the empty hash table of size 10. So to start off with, we take 89 and 18 we take mod of both, which is 9 and 8. Since 8th and 9th location are free, we place 89 and 18 in their respective slots. So the next number is 49. We take mod 10 of 49, which is 9. So originally it should go in the 9th slot, but there is a collision. So after that, we will probe the next location, what is the next location we will be probing? That is 1 square. 1 square is 1. So we'll probe the first location after 89, which is 0. It is empty. So we place 49 in this slot. The next item is 58. We take mod 10 of 58, which is 8. We have a collision here. So the first probe we will be doing is on the first 1 square location. So 1 square location after this point is this, which is also occupied. So after this, we will probe the 2 square location, which is 2 square is 4. So we will see the fourth location from this point, which is 1, 2, 3, 4. So this slot over here is empty. We will place 58 in this slot. Similarly, the last item is 9. We take mod 10 of 9, which is 9. So there is a collision. First we will look at 1 square location, which is this slot. It is occupied. Then we will look at 2 square location, which is fourth location from this point. So 1, 2, 3, 4. So the fourth location is from that 9th slot is empty. So we plug in 9 in this slot. So to summarize, when a collision occurs, we will be probing the first location will be 1 square, then 2 square, then 3 square, and so on. One of the issues with quadratic probing is that we may not find a vacant spot, while linear probing always finds an empty slot. So the table must be less than half full, which means that the load factor should be less than half. Another issue is that we may not be sure that we will probe all the slots in the table, since we are not looking at the consecutive empty slots. If the hash table size is not prime number, this problem will be much severe. However, there is a theorem stating that if the table size is prime and the load factor is not larger than half, all probes will be to different location and an item can always be inserted. Quadratic probing requires the multiplying operation and the mod operations. We can speed up these computations by using the following trick. Instead of using the multiplying and mod operations, we can always reuse the previous hash value that we have taken of the probe plus 2i minus 1, and we take mod of that. It will give you the next value of the key. In quadratic probing, if the load factor gets too high, we dynamically expand and double the table size as soon as the load factor reaches half. Remember to always double the table size to a prime number, and we refill the new table by using the new hash function. Quadratic probing does not suffer from primary clustering, since there is no problem with keys initially hashing to the same neighborhood. But it doesn't help if the keys initially hash to the same index, as they will probe the same alternative cells. This is called secondary clustering. Using probe functions that depends on the key can avoid secondary clustering. This technique is called double probing or double hashing. The idea of double probing is that given two good hash functions h and g, it is very unlikely that for a given key the results of both of these hash functions will be the same. So we can use one of the hash function as the original hash function and the other hash function as the probe function to determine the offset in case of collision. The I here represents the probe number and we will keep incrementing it until an empty slot is found. Now let's see how we will find the probe sequence. So initially we will just use the actual hash function. On collision, the first probe will be to the original hash of the key plus the probe function hash of the key mod m. If again there is a collision, the next probe will be to hash of key using the original function plus 2 times the hash of the key using the offset function mod m. So here we are incrementing the value of I. So in the next probe it will be 3 and so on. In the ith probe it will be hash of the key using the original function plus hash of the key using the probe function times I, which is the ith probe modulus of m. Make sure that your probe function will not result in the value of 0. As in that case, all the probes will be to the same location. Let's have a look at this double probing example where we have two functions. The first function is used as the original hash function and the second function is used as the probing function. So to find the probe sequence, we will have the following function where we'll be using the original hash function plus I times the probing function. I here represents the probe sequence or the number of probes made so far. Since our table size is 13, we will be using mod 13. So we have this table in which a few numbers have already been inserted. Now we want to insert the key 14. So as a 0th probe, we will use the first hash function and plug in the 14 here. So 14 mod 13 is 1. 1 is already occupied. So we'll have to find or probe another location. For that, we will use the following function. Since it is our first probe, I will be equal to 1. So we'll have hash with function 1 of 14 plus 1 times hash with function 2 of 14 mod 13. So this value here is 1 and this value here will be 4 since we plug in 14 here. We will get 14 mod 11 plus 1. So that is 3 plus 1 and that is 4 here. So we solve this, we'll get the value of 5. So our next probe will be to the 5th location. This is already occupied. So we will find another location or probe another location using this function by incrementing I. Now the value of I is 2. We solve for this again and we have the next location of 9. So we see the 9th location here which is empty. So we will insert the key 14 in the 9th location. The intuition of double probing is that since each probe is jumping by the value derived from the probing function each time, we leave the neighborhood and go different places from other initial collision. Just like quadratic probing, there is still a chance that we might not probe all the slots in the table. The disadvantages of double probing is that it is harder to delete an element and it can generate a maximum of m square probe sequences. The following plots show the efficiency of collision resolving strategies with increasing values of load factor. We can see that for both successful and unsuccessful search, the average number of probes in linear probing increases drastically as compared to others. For separate chaining, even at load factor of 1, the average number of probes is less than 2. To summarize, the hash table is one of the most important data structures. It supports only find, insert, and delete operations efficiently. It is really important to use a good hash function. It is important to keep hash table at a good size, that is, use prime number as a table size and a correct choice of load factor. For separate chaining, the load factor should be close to 1, and for open addressing, the load factor should not exceed half unless this is completely unavoidable. Rehashing can be implemented to grow or shrink the hash table. Hash functions have uses beyond hash tables. For example, they are used in cryptography as well as checksums. I hope you have enjoyed today's lecture on hashing. Thank you and have a nice day.